Afternoon, I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest video. Now, in this video, I decided to look at La Ninas and the North Atlantic hurricane seasons. As you can see on this particular slide here, the title slide, I'm showing you a very impressive hurricane at this point with a very well defined eye. And then surrounding that eye, we have the eye wall itself, which really has some very tall thunderstorm type structure, very tall clouds around this eye. So this is a really impressive view, satellite view of a hurricane. Let's go ahead and take a look at today's video. I'm going to start things off by defining a couple definitions, kind of talking about the ingredients that are necessary for tropical cyclones to develop. So let's go ahead and start with that first, and then I will end the video on the discussion of past La Nina summer, late summer, and early fall seasons, and what the numbers look like on those particular years in which we have La Nina in place. First of all, what is a tropical cyclone? This is a warm core, non-frontal, low pressure system of synoptic scale that develops over tropical or even subtropical waters that has a definite organized surface circulation. All right, let's break down some of these terms here in the definition of a tropical cyclone. First of all, when we say warm core, what exactly does warm core mean? This means that we have the warmest temperatures at the center of this system. So as you go inward towards the center of a hurricane, tropical cyclone, you're going to get the warmest temperatures within the center of it. Non-frontal basically means that this system is not associated with any type of frontal boundary. And of course, a lower area of pressure definitely going to be associated with lower pressure. As we know, some of the most intense lower barometric pressure readings are associated with tropical cyclones. All right. Additionally, we have other key terminology. So let's take a look at tropical wave. Now, this is just simply a trough of cyclonic curvature maximum in the trade wind easterlies. All right, so in the tropical areas, we have two zones of winds that are known as the trade wind easterlies. When I say two zones, I'm talking northern and southern hemisphere. So in the northern hemisphere, we have the northeasterly trade winds, and in the southern hemisphere, we have the southeasterly trade winds. So generally, the general wind direction in the tropics is from the east. With a tropical wave, we get this cyclonic curvature to the wind field. Tropical waves tend to reach maximum amplitude in the lower to middle troposphere, and they may or may not be accompanied by thunderstorm clusters. So tropical waves, you might not see much on a satellite image. You may not see that distinctive thunderstorm cluster area. With tropical waves, the majority of them do not spawn tropical cyclones. These could just be little disturbances within the trade wind easterly wind belt, and they may not spawn any tropical cyclones at all. In the passage of these waves, if you're anywhere in the tropical areas living, you may have noticed these passing through from time to time. And the passage of these tropical waves is often accompanied by squally-like weather. So a condition in which you get a really heavy burst of rain on short order, and then kind of gusty winds associated with that heavy burst of rain showers. And then before you know it, you don't have any kind of squalls at all. The weather is dry again. So with the squally type weather, these rain bands, rain showers, you get these higher gusty winds as well as higher sustained winds. From my experience, I've actually been down in the tropical areas of the world. And I remember this one time, I was running a 5K ride. I was running a 5K race. It was just a fun 5K. And all of a sudden, just we're running the race, and all of a sudden, this squall just passes through this tropical location I was at. And I swear, I went from sunny to basically just heavy downburst of rain, like within 2 minutes. And then just as fast, the rain shower ended. And that's very typical type of weather when you get these tropical waves passing through locations in the tropical areas. And a lot of times in the tropical areas, they'll use the term liquid sunshine because you'll get some of these tropical downpours, but you still may have the sun out. It's kind of weird. Here's an example of a tropical wave on a satellite image. And notice, you do have some clouds here represented by the white coloring here. These are your clouds. And here's the tropical wave axis right here, this orange line. And so, you're going to get some showers and some squally weathers perhaps associated with this as this tropical wave. It's going to move from east towards the west because we have the easterly trade winds. Here, let me draw this for you. Let me draw this out. Okay, so when we are in the tropical wind belts, we have some of these northeasterly trades in the northern hemisphere. In the southern hemisphere, it would be more from the southeast, but generally these weather systems in the tropics are going to move from the east toward the west, opposite of what we get in the mid-latitudes where we have the westerly wind belt. So, but you kind of see the outline of all the clouds. They're not very organized, are they? More of an extension or elongated appearance on this satellite image. All right, so now let's talk about the next key term, and we'll talk about a tropical disturbance. So let's go back to this. So what is a tropical disturbance overall? It's a discrete tropical weather system with apparently organized convection, generally 100 to 300 miles in diameter, originating in the tropics or subtropics. With a tropical disturbance, it also is not associated with a front. So it's non-frontal migratory character. It maintains its identity for about 24 hours or more. Tropical disturbances do include some of the terminology such as tropical waves, surface troughs, which are those areas of lower pressure, and dissipating frontal boundaries. So in some cases, you get frontal boundaries to kind of come down into the tropics from the mid-latitudes, and they kind of just stall out in the tropical waters over very warm waters, and you can get disturbances associated with these dissipating frontal boundaries. And tropical disturbances also do not have a closed surface wind circulation. Here's an example. This is of a tropical disturbance. This is the 2-day graphical tropical weather outlook from the National Hurricane Center in Miami. Notice with a tropical disturbance in general, again, it's not exactly very well organized, right? In this case, we had a 0% chance of development with this tropical disturbance. But in general, you're going to see it move from east to the west, following those easterly trade winds. Those easterly trade winds are pushing this along. But you are going to get, your fair share, with a disturbance. You're going to get some fair share of tropical downpours and, unsettled weather as this thing passes through. Next, let's talk about what's known as a potential tropical cyclone. Now, this was very confusing to me at first, when the terminology first came out, when the National Hurricane Center and NOAA in general would classify these disturbances in the tropics as potential tropical cyclones. It's a term used by the National Weather Service to describe a disturbance that is not yet a tropical cyclone, but it does pose a threat of bringing tropical storm or hurricane conditions to any land area within 48 hours. National Hurricane Center will give the disturbance a number. There'll be complete advisory packages issued for it. And generally you'll have watches or warnings that'll be issued for the affected areas. So, a potential tropical cyclone, it's not quite to that category of being a tropical cyclone yet, but it could bring tropical storm force or hurricane force wind conditions to land areas within just 2 days. The next one we'll talk about is a tropical cyclone. Now, this is a warm core, non-frontal, synoptic scale cyclone originating over tropical or subtropical waters with organized deep convection. It has a close surface wind circulation as well, about a well-defined low pressure center. A lot of times, if you look at satellite imagery in the tropics, you can actually see the twisting to the cloud feature if you animate it, and that would be indicative of more of a well-defined low pressure center. Now, once formed, a tropical cyclone is going to act to remove a lot of heat from the very warm tropical waters, extracts a lot of heat from the ocean surface, and this heat is used as fuel. Tropical cyclone encompasses tropical depressions, as well as tropical storms, hurricanes, and typhoons in the western North Pacific. So tropical cyclones, they do, if we were to consider a depression, a storm, hurricane, typhoon, those are examples of tropical cyclones. If we continue the development process now towards hurricane status, we'll start first with a tropical depression. Now, this is a tropical cyclone with maximum sustained surface winds, 1 minute average of the winds of 33 knots, or if you were to look at it in miles per hour, 38 miles per hour or less. Once a system attains this depression status, the National Hurricane Center will assign it a number based on how many systems have received advisories in a given season. Now, if a named system weakens to a depression, the system will keep its name. So tropical depressions can have a number assigned to them when they initially develop. They can also have a name assigned to them, specifically if, let's say, we go from a depression status to a tropical storm or hurricane, and that tropical storm or hurricane then weakens back to a depression status, it'll keep the name of that storm. Now, here's an example of a tropical depression forming. We're basically east of Cuba, and you notice with this one here, we have a lot of clouds associated with this tropical depression. Now, I would need to see this satellite image in motion or animated to really determine where is the center of circulation of this thing. This is a very broad, unsettled area of weather. Like I said, it's just to the it's to the northwest of Puerto Rico, and it's to the east of Cuba. Next, let's move on to talk about tropical storm. What exactly is that? Tropical storm. We could go back here. A tropical storm is a tropical cyclone. It has maximum sustained surface winds, the 1 minute average ranging from 34 to 63 knots, or 39 to 73 miles per hour. Once a system attains tropical storm status, the National Hurricane then assigns a name to it. And so in this example here, you could clearly see the delineation of, a very nice center indicated here. I'm not even looking at this in motion, this radar, but you can see what is typical here once you get a tropical storm status is you get some of these banding features here wrapping it ahead of the main low pressure center, which in this case is right along the Florida Peninsula coast. But you get a lot of southerly winds kind of pumping up towards the coast, a little bit of elevated storm surge or elevated water coming into the coast in this example. But yeah, you see the very distinctive circulation though with this particular system. And then finally, we talk about hurricane. What is a hurricane? It's a tropical cyclone with maximum sustained surface winds, the 1 minute average, 64 knots or greater. If we're doing it miles per hour, it'd be 74 miles per hour or greater. It's known as a hurricane in the Atlantic, Northeast Pacific, as well as the North Central Pacific. But if you go to the Northwest Pacific, it's known as a typhoon. So it's the same type of storm, same classification, just depends on what region you're operating in. If we were going to the Indian Ocean, we call it a tropical we call it a cyclone. All right, when we talk about hurricanes in general, or tropical systems, cyclones, we have to look at what's known as a Saffir-Simpson intensity scale. And so you kind of see the breakdown from depression all the way to a Category 5 hurricane. And these are the wind speeds in knots. Okay, so you can see the wide range of wind speeds here from a depression to a Cat 5 hurricane. Now, there's other type of features that exist in the subtropics, and these are known as subtropical cyclones, and they also are not associated with any fronts. They have both tropical and extratropical characteristics. So they're not just solely, let's say, for example, a warm core system or a very symmetrical system. Maybe they're elongated, more asymmetrical in shape on a satellite image. So these are known as subtropical cyclones. They originate over tropical or subtropical waters. They do have a closed surface wind circulation about a well-defined center. And subtropical cyclones derive a significant portion of their energy from baroclinic sources. They're generally cold core in the upper troposphere and may be asymmetric or elongated. Now, what time of year do you expect to see subtropical cyclones? That's really going to be towards, most likely, the start of the hurricane season, as well as the tail end of the hurricane season. Now, the Atlantic hurricane season runs from June 1st to November 30th. Specifically towards the end of the hurricane season in the Atlantic, you have some of these mid-latitude type storm systems coming in off the United States. And many times you'll get some of these systems that spin up that have both the warm core and cold core characteristics, as some of the energy in some cases it gets absorbed by the mid-latitude westerly wind belt. So here's an example of a subtropical cyclone. Notice it's more it has more symmetrical towards the center of where the low pressure is, but you kind of see the elongation out ahead of it. This is covering a very large area, isn't it? And you also do not see the complete wraparound of the thunderstorms on the backside of it. So subtropical cyclones generally are going to be more elongated and again have cold core characteristics in the upper levels of the atmosphere. All right, so now that we discussed some of the key terminology, let's move on now to the hurricane key ingredients. What is necessary for hurricanes to form? All right, so let's take a look at these. This is the breakdown. I'm going to break it down further here in the coming slides, but at first we need a pre-existing surface disturbance with thunderstorms. We need a warm ocean, of course, that's the energy source. Low vertical wind shear. Wind shear is a change in wind direction with height, or it could be a change in wind speed with height. So you can have both speed and directional wind shear. And wind shear is bad for hurricane development because it tends to rip apart some of the growing cumulus clouds. Those growing tall vertical clouds, it distributes the energy over a much larger area. The hurricane wants that energy to be concentrated in a smaller area, not a larger area. So vertical wind shear is not a good thing. Higher vertical wind shear is not a good thing for a hurricane. Lower vertical wind shear or a lack of wind speed changes with height, lack of wind direction changes with height is very, very favorable. Unstable atmosphere is also a favorable ingredient. Got to have an area with high atmospheric moisture content, okay? A lot of times systems in the tropics cannot develop because you have the Saharan air layer, SAL. That's that dry air coming in off Africa. And sometimes those easterly winds will pick up that dry air and basically spread it all the way to the Caribbean. And what happens when you have that dry, warm air is it acts to choke off any type of updrafts associated with any type of tropical system. And, drier air entrainment, where that dry air gets entrained into a tropical system, is going to inhibit its potential development as well as its intensification. So Saharan air layer from Africa, a lot of dry, dusty air, not a good thing for a hurricane. You want a lot of high atmospheric moisture content. You also want a nice exhaust system above a hurricane, upper level outflow. So that has to do with that low vertical wind shear again. And then you also want an adequate Coriolis force, which is going to result in some type of spinning rotation or some kind of spinning motion in the tropics with a disturbance. All right, so let's break these down individually now and talk a little bit more about them. First ingredient was a pre-existing surface disturbance with thunderstorms. All right, so relying on that buildup of heat energy within the atmospheric column above these thunderstorms to grow and develop further. Thunderstorm complex is going to act as a vertical transport mechanism for that heat and moisture from the very warm tropical waters. It's going to cause the air to rise within the atmospheric column, and you're also going to get some of that cyclonic turning, perhaps, of the winds in the upper levels of the atmosphere when you have these this disturbance already existing in place with these thunderstorms. Warm ocean, another key ingredient. The hurricanes draw on that heat energy stored within the ocean. You want sea surface temperatures of at least 80 degrees Fahrenheit to support the development and intensification of hurricanes. A lot of times you'll see hurricanes, they'll be really strong, and then as they move poleward towards the north in the northern hemisphere, they start to weaken because they start encountering cooler waters that are below 80 degrees Fahrenheit. Or sometimes you get a case where you get one tropical cyclone developing and it tends to stir up the water, right? With all the wind energy, it really causes cooler water to come up from the depths, the deeper ocean depths to the surface. And then you get a secondary tropical cyclone going over the same path. Those water temperatures just aren't warm enough because of that greater mixing, bringing that cooler air up towards the surface. Additionally, with a warm ocean, evaporation of that warm water, that's going to act as an energy source to really energize the atmospheric column. Basically, when you evaporate the water, it goes from a liquid to a vapor, and then as the air continues to rise, eventually it cools, and condensation is achieved, where you go from a vapor to a liquid, and as that process occurs, condensation from a vapor to a liquid, it releases latent or hidden heat to the surrounding atmosphere, and that tends to destabilize the atmosphere even more when you release that heat to the surrounding air. and that results in even taller growing clouds. The mixed layer, the zone with nearly constant temperatures, should be at least 60 meters deep. Now, when we talk about the ocean surface, and the mixed layer is that area of the ocean in which we have a lot of mixing because of winds. So you don't want to have super cool water again coming up towards the surface. You want at least 60 meters deep of nearly constant, very warm tropical waters, preferably at least 80 degrees Fahrenheit. The next hurricane key ingredient, low vertical wind shear rather. That means little change in wind speed or direction throughout the depth of the troposphere. This is common in La Nina periods. Tropical cyclones are going to rely on vertically stacked structure to grow or maintain intensity. Again, they want the energy. Tropical systems really thrive on energy that is more concentrated vertically. And if you get any kind of wind shear, that's going to tend to result in destroying that area of concentrated energy. It's going to make it spread out over a much larger area. Changes in the environmental wind speed or direction with height will tilt the vertical structure of the system as well. And that vertical tilting of those rising columns of air is going to inhibit growth and may cause the system to decay. Unstable atmosphere, very important for hurricane development. Temperature is going to drop or decrease quickly with height in an unstable atmosphere. We call that positive buoyancy when the air temperature drops rather rapidly with height. The greater the difference in the temperature in the vertical column, let's say from the lower levels, let's just say the ocean surface up to about 10,000 feet. The greater that difference in the temperature, where you get very cold air aloft over a very warm surface, that's going to promote more vigorous rising air motion and stronger updrafts. And that's exactly what you want with unstable atmosphere. So that promotes that rising vertical air motion. That rising air, you want that to continue. It's needed. It's basically like a heat engine, a hurricane. It basically takes in low-level converging air. That low-level converging air rises, extracts heat right off the ocean surface, and that fuel is then lifted to great heights in the atmosphere, and then it spreads out aloft above the system where you have an exhaust mechanism. High atmospheric moisture content, all right, another key ingredient. Again, I talked about the Saharan air layer coming off of Africa. You do not want that dry air to choke off your updrafts or strong vertical rising air motion within the column. And if it's too dry, you're simply going to be inhibited or limited in your cloud formation. Without condensation, again, there's no latent heat. Latent referring to hidden heat, but it's so critical. You can't see it, you can't sense it, but latent heat as the source of energy from the ocean surface rises via that evaporation. Eventually, that air cools, it condenses, forms clouds. In the process of condensation, again, releases heat to the surrounding air, makes things even more unstable. And that allows, that latent heat release also creates and supports the warm core structure of a hurricane. If you look at the bottom right here, this is a cool thing. This is from the TRMM mission, Tropical Rainfall Measuring Mission, TRMM mission. This is showing you a vertical cross section of some of the hot towers. These hot towers generally surround the eye of the storm, or they basically are within the eye wall of these hot towers. There's a lot of heat being taken from the ocean surface. Check this out. Check this out right here. Okay, okay. There's a lot of heat being taken off the ocean surface. This air vigorously rises in the vertical. That's what we're showing you is a cross section of some of these hot towers, and the air is rising vertically. All the heat energy from the ocean surface is being redistributed throughout the whole entire atmospheric column, and it's really an impressive, just impressive thing to watch. The upper level outflow also very important. You know, we have increased wind shear, or let's say we get an upper level trough to move into the area. It's going to increase that wind shear, and it's going to destroy the overall structure of what you want for a hurricane. So you want lighter upper level winds is what I'm getting at. You want the exhaust mechanism. You can easily see this on satellite imagery where you almost see like an anticyclonic spin of high cirrus clouds over the top of a developing tropical system. That exhaust mechanism is needed above a system to perpetuate the strong upward motion. Like, you really do not want very strong winds in the vertical. You want very light winds. You want that nice high pressure system aloft over this tropical system to where it can further help to remove the mass in the upper levels of the atmosphere. And that's going to allow for the surface pressure to continue to fall. As a system develops, low-level cyclonic flow then pulls the mass towards the center. The flow then turns upward as intense vertical motion associated with thunderstorms. And this process actually has a name. It's known as the in, up, and out circulation. So again, this is a fine-tuned system, okay? This is just an impressive thing to watch, just from start to finish, from depression to a Cat 3 or stronger hurricane, just watching these type of things happen. And then you also want adequate Coriolis force. You need some type of spinning motion to that low pressure area. You want some type of cyclonic turning. And due to the Earth's rotation, the Coriolis force causes tropical cyclones to spin counterclockwise in the northern hemisphere, and they spin clockwise in the southern hemisphere. Now, this spin is a critical component for development and intensification of a hurricane. Tropical systems rarely develop within 5 degrees of the equator. There's simply no Coriolis force at the equator within 5 degrees of it, either side of it. Here is a great example. This is showing you all the tropical cyclones, generally where they form. You see there's a lot over here in the southern hemisphere as well. Indian Ocean extending eastward towards Australia and even east of Australia. I mean, look at all these. This is where they typically form in the southern hemisphere. You see this orange color here. This is quite a bit of strong tropical systems out here. You see the categories here in the bottom. That red coloring, the brighter orange indicates Category 5 storms, and there's quite a few in the western North Pacific there. Additionally, you see them in the eastern Pacific, tropical cyclones. You see them in the Gulf, the Caribbean, of course, the western Atlantic, which we're familiar with. But you'll notice this absence here between the northern and southern hemisphere. You noticing that? Right here. Because that has no Coriolis force. There's zero spin at this point. And that's why you see these systems forming either 5 degrees north latitude from the equator or 5 degrees south latitude from the equator, but nothing directly right on the equator. Here's a life cycle of a typical North Atlantic hurricane, by the way. You'll notice initially it comes off, let's say it comes off the coast of Africa here as a tropical disturbance. That tropical disturbance organizes over time, eventually forming a tropical depression. That tropical depression, if the conditions are really adequate, like we just went over the ingredients, if those ingredients are in place, it will strengthen further into a tropical storm, then into a hurricane, and then this thing is going to recurve to the northeast and basically become an extratropical cyclone at this point. It may take some 16 to 17 days later, but you'll have a conversion from a tropical system where it's symmetrical in appearance to a more asymmetrical appearance in satellite imagery, an extratropical cyclone. And then this thing just takes off in the mid-latitude westerly wind belt, just pushes it towards Europe, specifically northern Europe, towards the British Isles. So this is we have some key features on here. We have northeast trade winds. We have the prevailing westerlies up and off the United States. And so we have a lot of different features here, but this is the typical life cycle of a North Atlantic hurricane. Starts at low latitudes as a disturbance, becomes a depression, a storm, a hurricane, and then converts over to extratropical cyclone. All right, so before we really delve into the details here of La Nina seasons and North Atlantic hurricane activity, we need to basically describe what an average North Atlantic hurricane season is. Now, it's changed. The numbers have changed slightly here. We look at the 1981 to 2010 climatology. The average for the North Atlantic hurricane season was 12 named storms, 6 hurricanes, 3 major hurricanes. Now, major hurricanes are Category 3 strength or stronger. Now, we got to 1991 to 2020, the new 30-year data for the climatology, and now we have the average North Atlantic hurricane season features 14 named storms, 7 hurricanes, and 3 major hurricanes. All right, so some of the key aspects of La Nina and the North Atlantic hurricane seasons. During La Nina, the easterly trade winds over the Pacific Ocean are stronger, and these winds pull the top layer of warm ocean water westward. And as a result, we get cooler water that upwells itself along the South American coast that eventually gets pulled into the Central Pacific, that cooler water. This persistent cold water then creates large-scale subsidence or sinking air motion and reduced convection in the eastern and central Pacific. That pattern then affects global circulation by producing an upper level trough in the subtropical Pacific, but then it has a downstream ridge in the western Atlantic. Now that's key. Ridges are associated with much lighter winds aloft. Okay? And we talked about the importance of wind shear. We want very little in the way of vertical wind shear, and we get that with a ridge. As a result, wind shear is increased in the trough. Now, you're over the subtropical Pacific, you're going to have much more wind shear, but it's going to be decreased in that ridge over the Atlantic. And that causes decreased tropical cyclone activity in the eastern Pacific and enhanced or increased activity in the Atlantic. Again, lighter winds aloft are essential for increased tropical cyclone activity as well as survivability. Here is an example from NOAA. So in a typical La Nina year, you have fewer hurricanes in the eastern Pacific, stronger vertical wind shear there. You get cool and dry air, sinking air motion over this cooler than normal water. And on the Atlantic side, you get more hurricanes due to a weaker vertical wind shear profile. And the trade winds are weaker as well over in this part of the world. And there's less atmospheric stability overall. Here's wind shear in the bottom left. Just want to again describe it. You can get wind direction changes from the surface to aloft, higher above the ground. So directional wind shear can occur with different wind directions at different altitudes with height. You can get speed shear where your wind speeds dramatically change over the vertical layers. And you can get both, speed and directional shear at the same time. You do not want wind shear, okay? Bottom line, you do not want wind shear if you want more active hurricane seasons. So now I went back. Let's take a look at some of the data in the past hurricane seasons when we had La Nina conditions in place. I went back to 1995. So I went back, what are we, almost 30 years, right? 29 years of data. We took a look at those particular years in which we had La Nina conditions in place in the late summer into the fall and what happened with the hurricane season, okay? Starting with 1995 hurricane season, when we had La Nina in place, there were 19 named storms, there were 11 hurricanes, and we had an above average season overall in 1995. There was a couple really good ones for the Florida Panhandle in particular that really made some noise. Hurricane Aaron and Hurricane Opal. Opal was a late September, early October system for the Florida Panhandle, and those systems were very strong. You can kind of see the tracks on these graphics that are provided by the National Hurricane Center. But in general, you kind of see the legend here in the bottom right of each of these graphics. So whenever you see like the purple coloring or the magenta, that's a major hurricane, category 3 or stronger. Whenever you see the red coloring, that's just a hurricane, less than a major hurricane, so maybe a Cat 1 or Cat 2 hurricane. When you see the yellow coloring, that's a tropical storm. Where you see the green lines, that's a tropical depression. And if you see orange at all on here, that indicates a tropical storm. So this was 95, finished above average. We had La Nina in place. This is the 1998 hurricane season. We had 14 named storms, 10 hurricanes. It was another above average season. And you notice some of the tracks of some of these also is indicated by these lines. That particular year, 1998, 14 named storms. So went all the way from Alex to Nicole. Nicole formed as late as November 24th to December 1st. So that was a late system. 1999 hurricane season during La Nina conditions, we had 12 named storms, 8 hurricanes. We had above average number of hurricanes for that year. Remember, at this time it was 12-6. 12 named storms was average, and 6 hurricanes was the average based on the 81 to 2010 climatology. So we were above average in hurricanes by 2 hurricanes in the 1999 hurricane season. One of the bigger ones that really got people on edge was Hurricane Floyd back in September of 1999. That system in particular, let's see, I'm looking for the right track number here. It basically paralleled the Florida Peninsula, the coast of Georgia, and the Carolinas. It paralleled it. And it was a huge, massive storm. It was one of the largest evacuations for a tropical system in U.S. history at the time. La Nina now, in the 2000 hurricane season, we had 14 named storms. which is slightly above average, the average of 12 at that time. 8 hurricanes, slightly above average there. So an above average season overall. I'm looking at the list of names here to see, hey, which one of these was really making a lot of noise or was a major threat. You kind of see some of them had come inland a little bit here in the Big Bend of Florida. There was one. Another one came in to around the Pensacola area of Florida. But a lot more misses in this particular season. You see a lot of recurvature of these lines out over the western North Atlantic. The La Nina in the 2007 hurricane season. In this case, we had 15 named storms that season, 6 of which were hurricanes. So we had above average named storms in that season, 15 when it should have been 12. And you look at the overall tracks of some of these systems. We went all the way from Andrea to Olga on the list, the name list. We do see a couple close calls there near Outer Banks. We also do see a track coming in towards Florida. So it was very busy. There was another track that went into Texas as well that particular season. The La Nina and 2010 hurricane season, we had 19 named storms now. So that's well above normal. 12 hurricanes, well above normal, above average overall. But thankfully, we didn't have a lot of hits on the U.S. and not a lot of landfalls. There was one landfall from southern Florida into Louisiana in the 2010 season. There was another little tropical system that came in at the very southern tip of South Texas. One storm here, what was that? It got up to, this would be major hurricane status here off the southeast coast in this magenta line here, and the recurvature, though, it remained offshore, thankfully. The La Nina conditions in 2011 hurricane season, there were 18 named storms in this particular hurricane season, 7 of which were hurricanes. So we had above average season overall. You really see this close call to the East Coast, kind of passing up over the Outer Banks. That was 2011, right? That might have been Irene coming in. I remember this one. I remember this one because everybody was worried about Irene. And they were really worried it was going to go right over New York City, that 2011 hurricane season. And they were really worried about the flooding potential, specifically for some of the transportation systems in New York City. The subways in particular are flooding. So there was a lot of concern as this thing kind of paralleled the East Coast. It went right over the Outer Banks and then kind of remained just offshore, but it went up towards New York City. Thankfully, it weakened into a tropical storm by the time it got up to that latitude. La Nina conditions in the 2016 hurricane season. There's 15 named storms, 7 hurricanes, another above average season. Look at the cluster of storms here. Generally from Georgia coast up to South Carolina and North Carolina. This was a very active season of potential threats or impacts in that particular area. And you are more than welcome to go to the National Hurricane Center and view all these past seasons with these tracks and get more detailed information. But this was a doozy of a season. Now, I specifically remember Matthew, September 28th to October 9th. That was one heck of a system. It packed quite a punch. And just in the Hampton Roads, Virginia area, we got over a foot of rain over a matter of 2 days. It was insane, the amount of rain that was out in this area from Hurricane Matthew. But nothing really went up towards New England in the 2016 hurricane season. You see one coming in the Gulf there, the Big Bend of Florida, but nothing really from Pensacola westward to Houston or Galveston. No landfalls for those locations in that year. La Nina in the 2020 hurricane season. Now this was a whopper of a season, everybody. 30 named storms. It got so crazy that the National Hurricane Center had to go to that alternate the alternate naming list after they used the W storm. It went to Alpha, Gamma, Delta, Epsilon, Zeta, Eta, Theta, and Nota. I mean, it had to go to this alternate list because there were so many named storms. 30 of them. I mean, and at this point in time, that's insane. It's well above the normal. Not only were there way above normal named storms, but there were 14 hurricanes. And look at all the impacts here in 2020. Okay, look at how all these lines are intersecting the United States. Some are going up the southeast coast, the Mid-Atlantic. Big clusters formed in the Gulf and kind of taking that track through the Gulf of Mexico. I mean, this was a very, very active season for the Hurricane Center. Um, yeah, look at all these lines on here. I mean, just phenomenal, the 2020 hurricane season. La Nina, the 2021 hurricane season, slightly down from the previous year. Still 21 named storms, 7 of which were hurricanes, above average in named storms overall. Um, by this point, we had 14 was the average named storms climatologically. Again, you see a lot of intersections with the Gulf of Mexico, the Gulf states, systems coming in there. Particularly, we saw some systems also impacting some of the eastern U.S. with flooding rains. So, very interesting. And then La Nina in the 2022 hurricane season, not as many landfalls in the U.S. in this particular year when we have La Nina in place in 2022. We did get a couple systems coming into Florida as well as up towards, North Carolina. I'm trying to remember the storm. That might have been Ian coming in towards the southeast coast, but I'd have to dig a little deeper on that. But in general, you kind of see the tracks. A lot of them remained offshore in this particular season, but we were above average again. So here are my findings after taking a look at the La Nina conditions and hurricane seasons back to 95. I looked at these La Nina periods in the North Atlantic hurricane seasons. Again, I went back to 1995, so about 24 years worth of data. All of these seasons finished above normal for overall named storms, which we would expect. La Nina conditions, they're more favorable in the Atlantic sector. We have relaxed wind shear as an example. Named storms, by the way, in my research, the named storms range from a minimum of only 12 in 1999 to a maximum of 30, that crazy active busy season in 2020. So from 12 to 30 for the named storms, that was the range. Hurricanes ranged from a minimum of 7, 3 separate La Nina years, 2011, 2016, 2021, to a maximum hurricanes of 14 in 2020. Now, there are other factors, no doubt, that would favor increased tropical cyclone activity across the North Atlantic, in addition to the La Nina. Now, I just looked at the La Nina in this video. So, for example, warmer than normal sea surface temperature. We have cycles that are associated with what's known as the Atlantic Multidecadal Oscillation, AMO. Certain times or cycles, there's warmer than normal waters across the Atlantic, and that's an association with the AMO. So there's other things that could also contribute to increased activity, such as the 2020 hurricane season. Now, I did not examine the landfalling tropical cyclones. I didn't really delve deep into, how many La Nina seasons feature, does La Nina in general feature more landfalling tropical cyclones into the U.S. or not? So I didn't really look at that. I didn't look at those tendencies either between La Nina years versus other years. I did not examine the tropical cyclone intensities during La Nina versus non-La Nina years. I didn't look at the intensities of these either. So further research definitely needs to be conducted for both, examining those landfalls as well as the intensities in La Nina versus other years. I just wanted to put together this video. I thought it was interesting. Just taking a look at La Nina. We all generally know La Nina tends to favor increased activity in the Atlantic. This year, in the outlook that was issued by NOAA, Colorado State as well, we're expecting above normal hurricane activity in the Atlantic and tropical cyclone activity in the Atlantic because we have a La Nina coming on, plus we have just absurdly warm ocean temperatures over the Gulf, over the Caribbean, over the main development region of the Atlantic. So there's a lot that goes into hurricane forecasting, and La Nina is just one of those factors that leads to increased activity. This, by the way, to end, is this was a hand-plotted chart of a hurricane. This was I believe the 1900 Galveston hurricane. This is when it was over right around the vicinity of Jamaica. Just really impressive, the fact you can go back to look at these old charts like this. I think it's cool. It kind of shows each of these like red isobar lines represents equal barometric pressure. The lowest, of course, towards the center of this tropical system. I just think it's really interesting. I like to look back at old school charts like this. Anyway, that's all I got for now. I hope you enjoyed this presentation. I'll be moving on to the training series here shortly. So I'm looking forward to that. a lot to talk about, a lot to watch in the upcoming hurricane season for sure, with La Nina coming on. So that's all I got for now, everybody. Until next time, take care and God bless everyone.